I'm sure like most people are familiar with Clara and Steve, but just in case that you're not, Clara is the head of the climate analysis section of CDG, and she studies like the global climate variability and especially like the interaction between atmosphere, ocean, and the sea ice. And she is a member of the National Academy of Sciences and we're also HU and AMS member. Steve is a project scientist at Climate CCR section of CGD, and his focus is mainly on the large-scale ocean dynamics and more so the global climate variability and predictability on the seasonal to decadal timescales. Today, they're going to give us a joint seminar on predicting El Nino in 2023 and 24 and its climate impacts over North America. Without further ado, let's welcome our two speakers.
Thank you so much, everyone, for coming a little early. And it's a real pleasure for me anyway, to step into some new realms here with predictability and to do this jointly with Steve. And I want to give a very big thank you to Nan and Adam. This project happened very quickly, and without them, we wouldn't be standing here today. So really appreciate all their efforts. And then we had a lot of great discussion and input from these other people. So it's very nice to be able to share with you work in progress about predicting this El Nino and its climate impacts over North America. So I got interested in this back in late October. So this is all very, very recent. And of course, the interest was spurred by this prediction of the super El Nino. We'll hear more about that from Steve. And I thought, well, for many, many years now, I and others have been studying how well the atmospheric model does at simulating ENSO teleconnections and how those atmospheric teleconnections impact climate over North America. And we had many papers, including these two, and I think we're quite had our eyes opened about that it's actually really hard to even robustly detect some of these ENSO signals over North America in terms of precipitation and air temperature because of internal variability in the atmosphere, which then competes with these ENSO-driven teleconnections. And that then leads to this need for large ensemble sizes to even evaluate how well atmospheric models do when given the observed SSTs, how well they can simulate ENSO teleconnections. So I had that knowledge base, and then Steve with the predictions, and we just decided, or I decided, I guess I initiated this project, we should do a handoff here, and we should really then maybe enhance what the information we obtain from these SMILE forecasts by using kind of a two-tiered approach where we take the predicted SSTs from the coupled model and then specify them to the atmospheric model, and then we're able to run very large ensembles and also importantly to understand, to attribute the forecasts. What are the physical reasons for these forecasts? So that's how the whole project got started. So before I hand it off to Steve, I do want to say that I think, we can have quite a bit of confidence in the CSM2 SMILE and the atmospheric component model. In this pair of papers, we actually analyzed CAM5 simulations. Today we'll be showing you CAM6. But I just want to say that we did a lot of work and showed that, or just demonstrated that CAM5 is able to simulate realistic impacts over North America to the observed composite SSTs from historical El Nino events. So I think this is a very fruitful partnership, and I think there's so much more to dig into, and we can just present the beginning of this collaboration here. Okay, so Steve is going to take over and talk about the actual SST prediction, and then I'll come back and I'll talk about how we then try to probe the impacts of those SSTs.
Hi, everyone. I want to start by just thanking Clara for her initiative and leadership in getting this project started, and also for agreeing to give this seminar, which I asked her in late November, thinking March is a long way off and we'll have plenty of time to show some results by then, but it came up quickly. And most of the people in this room will be familiar with SMILE, but there may be some people in the audience who will need this little primer here. We put together this seasonal to multi-year prediction system using the CSM2 model and put this out to the community in 2022. SMILE is a seasonal to multi-year prediction system, so we're initializing quarterly every November, February, May, and August. We've done this all the way back to 1958 now, although the paper just analyzed 1970 onwards. And we're looking out 24 months into the future. So this is sort of an extended seasonal forecast range using 20-member ensembles. And what we showed in this paper is that, much to our delight, the SMILE system shows skill for ENSO that's really competitive with leading operational systems. And I'm showing you the skill here going increasing lead time from the top left down all the way to 19-month lead time here on the lower right. And certainly when we're initializing 1 month in advance, no surprise that we have quite good skill at predicting DGF and Nino 3.4, but you can see that skill persisting out to rather long lead times. And even at 19-month leads, we have some decades when we have this impressive extended predictability. We show in the paper that we are on par with the NMME multi-model mean skill when we initialize in August, and we're only slightly worse than the ECMWF seasonal system. So we're really delighted, because if you have a skillful prediction system, that means you've got a really powerful tool for doing the type of work that Clara is now spearheading. So around June or July of last year, Yeager came into my office and said, we should do a real-time forecast, because, of course, it was general knowledge at that point that Nino looked like it was developing, so we had a system that was skillful initializing in August, so we decided to do that. And this result that we got of a very large event for 2023-24 was shocking, and we had to think, what are we going to do with this? Should we sit on it? Should we share it with the working group? We decided to put it out to the community, to the UCAR community, in particular the CESM community, to showcase that we're doing this, we can do this, and we have the ability with the CESM model to do really topical science in real time. So what we produced with that forecast was a prediction of this very strong event. Our predicted anomaly for DJF was 2.32. You can put that in the context of some of the big past observed events here. And you also get a sense of the observational uncertainty. This first value is from HAD-ISST, the second value is from ERSST-V5. So this, there we go. So the event we were predicting looked like it would be on par with these three big events of the past 50 years. And when we compared it with kind of existing knowledge at the time, so the IRI plume of predictions, both dynamical and statistical, initialized from August 1st of 2023, you can see that there's quite a large spread for the prediction of DJF Nino 3.4. I can't use that. But we were certainly well within that spread, a little bit higher than the dynamical multi-model mean, but we had good company. We had ECMWF here and GFDL Spear also predicting an anomaly above 2. So it gave us a little bit more confidence in putting this out there. Then time passed and we got to November and initialized a new forecast, and our predicted DJF anomaly was weaker. It's now below 2 at 1.96 degrees C. And so from here on out, we'll be focusing on SMILE in November, the November 1st initialization of 2023. You can see the plume that we got from that November 1st initialization. This was the information that we had available at the time. We had observations that were slightly warmer than the forced ocean simulation that we're using to initialize the coupled prediction system. And you can see how that El Nino is developing, peaking in January, and then with our extended forecast range allowing us to get a glimpse into next winter as well, with fairly high probability of a La Nina for the coming year. And then we're also able to compare then to what other systems were doing when they initialized in November. And now you can see that the multi-model mean of about 2, very much in line with what we are predicting for DJF. There's still quite a large spread across the different prediction systems, even initializing in November. So one of the things that we know about SMILE is that we've got quite good skill at predicting tropical SST, particularly in the Pacific, but we've got much lower skill for climate impacts over land. So you can contrast these two figures showing you.
I think you skipped that part where we show the odds.
Oh, you're right.
Yeah.
I did. Sorry. Thank you for that.
Yeah, you're welcome.
Yeah. So I had a second version of this slide where I've updated it now with the latest observations. So now we have ERSST extending out through February, so out through last month, and you can see that the observed anomaly peaked earlier than we were predicting, and so that is giving us this warm bias in our prediction. If we compared NDJ, we might do better, but we were focusing on DJF. So the ERSST DJF anomaly that has now been observed is 1.1. Thanks.
It's a good forecast.
Yeah. So we have some skill at predicting SST, but we're much less confident in being able to say anything about what will be the impacts associated with this event, because our hindcast skill for things like precipitation over land is quite low, even at the first of the month. However, we also know that we have some suggestion that there are forecasts of opportunity during these strong El Nino events. We can look back at these past strong events from SMILE on the left here. I'm showing you predictions of seasonal precipitation, NDJ, initializing in November. And then you can compare it to the observed GPCP anomalies on the right. And I'll give you a moment to just look at these maps, but you can see that during these strong events, we have some skill at getting some of the character of the precipitation anomalies over equatorial Africa. We have some skill at getting this precipitation dipole over South America, and even some hints that we may be able to predict some of these regional patterns over North America, although of course this is a cherry-picked result. It's suggestive that maybe during these strong events we can trust SMILE more than on average. And here's the current event. So now we've got the NDJ SMILE prediction for precipitation for this year, for this winter. You can see that we were successful in predicting this strong positive precipitation anomaly over equatorial Africa that has been observed, and there's been coverage of flooding in Kenya and Democratic Republic of Congo that could be related to this ENSO-driven precipitation anomaly. But in other regions, not so skillful. In fact, our skill or our forecast over South America looks like it was a bust. On the other hand, this area of low precipitation in the southeast U.S., there's some hints of it in SMILE, but it's a very weak signal. So perhaps we have some skill. It requires further analysis to really tease that out. But what I want to show you before I hand back to Clara is that one of the reasons that we might have poor skill at predicting impacts is that, of course, the ocean model is developing bias during the course of the predictions, and we often sweep that under the rug. But what I'm showing you here is the actual evolution from November through February of SST anomaly from ERSST v5. So you can see the development of El Nino in November and December, staying largely the same magnitude and then starting to slacken off and really weakening again in the last month. And then the middle column shows the raw SMILE SST forecast. And in this plot, I've kept in the background model bias because I'm showing you the anomaly relative to observed climatology. So you can see that SMILE is certainly predicting the development of this El Nino event, but there's a lot of error that comes from a variety of sources, giving us this SST forecast error that you can see in the right column, which is simply the difference of the two leftmost columns. So again, the error is quite low here in the central equatorial Pacific because we're predicting the El Nino, but we have a lot of SST error elsewhere that comes from, we can think of that as coming from three sources. So we have a lead-dependent bias in the SMILE SST climatology, we have a lead-dependent bias in the trend, and then we have lead-dependent error in forecasting non-trend anomalies. So Clara's great idea is that let's get rid of these errors that we can get rid of by switching to AMIT mode. So these first two errors we can get rid of by taking our SST field, which is a climatology, a trend anomaly, and a non-trend anomaly, and just swapping in the observed climatology and the observed trend, and just using SMILE non-trend SST anomalies. So in that way, we can eliminate climatological SST error as well as any errors that come from misrepresentation of the trend. And then for the third source of error, we've come up with this method through discussion, and there's probably room for improvement here. But what we're doing is we're rescaling the non-trend SST anomalies by a multiplicative factor, and that SST factor takes into account our hindcast performance. So we're weighting it by the anomaly correlation coefficient at each grid point. So if we have low ACC, we're going to have a relatively low SST factor. We're going to damp those predicted anomalies. And then we're going to amplify our predicted anomalies with this ratio, which is the observed standard deviation at that point divided by the SMILE standard deviation. We call that the rescaled SST anomaly. And that's what I'm showing you in the fourth column here. So these are our sort of post-processed predicted SST anomalies as a function of a month from November through February of this year. Again, the numbers give you the Nino 3-4 index. Now you can see that we're no longer grossly overestimating the magnitude of this event. If anything, we're under-predicting it. But this is the real key. The far right column shows the forecast SST error after we do this post-processing. And you can see the dramatic reduction in error compared to the third column, which is sort of what the coupled model in SMILE is actually seeing. So now we've got a forecasted SST product that we can show performs better in hindcast mode, and we think is more appropriate for forcing AMIT runs in this sort of forecast mode. So with that, I'm going to hand back to Clara.
Sounds good. So I did want to say, I forgot to say at the very beginning, when we initiated this project, there was very little time. to do these runs, and I wanted these AMIP runs to be done before we knew what the real world was going to give us. Like, this was a true test. As someone put it to me, skin in the game. Like, okay, put, you know, our knowledge and all the diagnostic analyses that we've done for so many years, and then really put them to the test with these predictions, and doing it before we had any inkling of what the real world is giving us. Because who knows how that creeps into our thought process, and then, you know, really is not a fair, a real test of these predictions. So November 1st, they did the new predictions, and the Nino 3.4 came down to just below 2 degrees C. And so we did our first set of AMIP simulations, which I'll describe just here in a moment, during the month of November. So this was very fast track, again, thanks to Nan and Adam for accomplishing that. And so what I have to show you is really, very independent information from what the outcome that we are now seeing as we speak, before we knew what that outcome was. Okay, so the handoff here, as Steve has just described, we've taken these bias-corrected, that's what I'll call them, or rescaled, SMILE ensemble mean SST anomalies. So that's the predictable part of the SST anomalies from the coupled model, initialized 1st of November of 2023. And we specify them to the atmospheric and land model, CAM6, 1 degree resolution, the same as used in SMILE. And we also specify the same radial forcings as used in the SMILE forecasts. And we run 50-member ensemble. We actually ran them from November through June. So these are 8-month runs, and we have 50 of them, just perturbed by slight changes in the initial conditions. And I've just, in my own words, I think it may be helpful to just quickly repeat. So we've taken these SMILE SST anomalies and removed the SMILE trends from the hindcast. We applied that bias correction or rescaling procedure, and then we add those up to the observed mean state and the observed trend. And the observed trend we've evaluated from 1979 to 2019, and then we linearly extended that to 2023. It's a detail. We're going to update it to actually do the whole trend through 2023. So we're including the observed trend and the bias correction. And I just want to say that many people know that the observed SST trend in the tropical Pacific has presented a bit of a surprise or a conundrum, and you'll see that showing up in some of these results. So I think we were all especially interested in whether there was a role for background climate change or changes in climate on the El Nino teleconnections and the impacts over North America. So a really nice piece of this very nimble AMIP protocol is that you can run these things so quickly. So we decided we wanted to do a counterfactual AMIP ensemble. And so for our counterfactual, we are, in a nutshell, taking these rescaled SMILE SST anomalies and putting them into the observed world in 1979. So that's before, this SST trends have taken place from 1979 to 2023. So we're now, and we're using 1979 radiative forcings. So the same El Nino prediction, but now putting it in a climate of the observed climate of 1979. And then we have to have some control runs, otherwise we can't assess the impact of these SST anomalies. So we did rather idealize control runs. I think there's some room for improvement here, but at this point, this is what we've done. So we've just repeated the AMIP runs here, but not adding the SST anomalies. So it's just a repeating seasonal cycle of SSTs that were used for the actual experiment, and kept the radiative forcing the same and run 50 members. So that's our control against which we can assess the impact of the SMILE predicted SST anomalies. And then we need another control for the counterfactual, and that's along the same lines where we don't apply any SST anomalies in this counterfactual world. We keep the radiative forcings at 1979 and run another 50-member ensemble. So this is our setup to address not only the impacts of the predicted SSTs, but how they might have been modified by climate change. So if you, I'll just walk you through, so with this four sets of AMIP ensembles, we can address many things. One is if we difference the actual and the counterfactual, we can get at what the impact of the observed SST trends and the change in the radiative forcing from 1979 to 2023 is on the ENSO teleconnections and impacts. And then with these two control runs, we can isolate what the impact is of just the radiative forcing. And that's going to be some of the results that I find particularly interesting. Okay, so now we'll get on to results. And I'm going to focus here on SST and precipitation and sea level pressure. We've also looked at air temperature. I don't have time to show that. And I've looked at upper level geopotential height as well, but I don't have time to show that here. Okay, so here is the map of basically from Steve's, what he showed, but just a different color bar. So these are these rescaled SMILE predicted SST anomalies that are put on top of the observed SST trend from 1979, and they have, I'm comparing it against the 1979 control run, so they also have, there's also going to be the influence of the change in radiative forcing, not on the SSTs, but in the response. So that's our experiment, basically, and that's the 50-member ensemble. So that's what it looks like. Here is the precipitation response. So this is the 50-member ensemble mean, so I think it's a good handle on where we have a significantly different response from, you know, any change that's internal to the atmosphere that we get from the control run. So where you see the stippling, the dots, that means that we cannot, we don't have evidence that the response is significant. So the colors are showing you kind of a familiar pattern, and it does look quite similar to the SMILE of changes in the tropical precipitation and also some impacts in the extratropics. I will zoom in on North America in a moment, but I'm just showing you the global maps at the outset. And then on the right there is the sea level pressure response. And this looks a lot like the SMILE, 20-member predictions. And that's what really surprised me. And in particular, when Steve showed me the results from SMILE, I said, wait, that doesn't look like our canonical ENSO response, which is a deepening of the Aleutian low. It has that funny kind of high pressure ridge sitting over on the west coast there of Alaska and British Columbia. So that was quite a surprise. It's obviously significant relative to our control run. So that's an aspect I'll show you. We've kind of tracked down why that pattern is happening. Okay, so then we'll look at the counterfactual. So now, if this El Nino had happened back in 1979, what would the teleconnections and impacts would they have been? So here you're seeing the SST anomalies without the observed trend. And that is a very familiar El Nino-like pattern. I'm not going to show you the observed composite, but it looks very much like the observed composite. And here's the precipitation response to that counterfactual experiment. Little bit, there are differences, and we'll get to that, but not too apparent in the tropics, but we'll see that in a moment. And then here is the sea level pressure, and that's what I was expecting. That's the Aleutian low that we have seen over and over again for past El Nino events. And so the question was, why wasn't it showing up either in the SMILE or these AMIP ensembles? So now we can have fun and look at differences to try to attribute these forecasts. What are some of the physical factors that are behind, especially those differences in the atmospheric circulation, which then drive impacts downstream over North America. So this map on the bottom is, so I'm just taking the difference between the top and the middle. So this bottom one is then explicitly isolating the effect of the observed SST trend, and then for precipitation, sea level pressure, also the change in radiative forcing. So this is the observed SST trend from ERSST V5, and it has this cooling in the eastern half of the tropical Pacific. That is something that is a bit puzzling how to attribute that, whether it is a forced signal or there's some internal variability or some combination of the two. I think it's still an open question, but it's really important for how it affects the total impacts from this El Nino. So here is the precipitation and response to these SST trends obtained by differencing those upper two maps. And I'll draw your attention to the tropical Pacific precipitation, which we know is driving to a large extent the atmospheric circulation teleconnections to the extratropics. And what you can see in this tropical Pacific region is kind of a bit of a cancellation here in the precipitation. You have drying in the central Pacific due to this strengthened SST gradient, not a surprise. And then the El Nino itself is giving you enhanced precipitation in the tropical Pacific. So they're counteracting one another, although the El Nino effect is stronger. So now the interesting thing is to difference these sea level pressure maps. And now you can see that the map on the top is this superposition of these two opposing signals. We've kind of saturated the color bar here so you can't see the nuances, but to a large extent there is cancellation between the effect of the observed SST trend and radiative forcing change and the effect of the El Nino itself. And then that gives you that upper map in the upper top for the sea level pressure, which is a kind of small residual of the two. And I think that to me was just eye-opening and something to be, just important for its impacts on the teleconnections. And then I did want to note that the SMILE predictions and also these AMIP predictions are showing a large signal over the North Atlantic, kind of NAO-like, but not quite. And again, there is some cancellation between the effect of the trend portion and the effect of the El Nino itself. So again, these are very interesting, complex interplay of these two components. So now we can take this apart a little bit from the way that we've set up our control experiments. So we can now address what is the role of the observed SST trend versus the role of radiative forcing changes. And we can do that because I showed you we have those control runs. We just we hit the radiative forcings, and then we can subtract that from this lower map. Okay, so I'll walk you through what that looks like. So again, this is what you've just seen. This is the combined effect of the observed SST trend and the change in radiative forcing. So now we'll look at the effect of just for sea level pressure, how these two factors impact the pattern. So you can see that the high pressure response over the North Pacific is largely driven by the SST trend, and I think we can trace that back to, in large part, to the this drying in the tropical Pacific that goes along with the enhanced SST gradient. So I think physically that is a plausible chain of events. But there is also a role for radiative forcing. And in particular, in this North Atlantic sector, where you see the radiative forcing change dominates the total. So we do have to pay attention to that. And then in the southern hemisphere high latitudes, radiative forcing is obviously a very dominant contributor. And I would speculate that that's due to both changing greenhouse gas and the ozone depletion that's especially in this DJF period is causing that sea level pressure response. And then we can look at precipitation. Most of the precipitation change, I'm sorry that I don't have stippling in the middle maps, we just hadn't gotten to it yet, but most of the precipitation change is due, in the tropics especially, is due to the SST trend. But there are some impacts of radiative forcing, mainly in the North Atlantic and the southern hemisphere high latitudes associated with that sea level pressure response. And then an interesting signal over equatorial Africa that appears to be coming from the change in radiative forcing, as well as the change in SSTs. Okay, so that's a bit of trying to attribute these forecasts and trying to understand their patterns. Now I'm going to move to focusing on North America and in particular on precipitation. So we're going to see the same kinds of maps, but I'll try to take it apart and do a little bit more detail on the probabilistic forecasts of these impacts. Okay, so here again it's the same sequence. The top is the El Nino plus the observed SST trend plus the change in radiative forcing. So if the model is skillful, we might see that, unless internal variability will cover it up. Then the middle is the counterfactual. So if this El Nino had happened back in 1979, that is the impact. And then the bottom is the effect of the trend, observed SST trend and the radiative forcing. So we can just look at a few areas, and I think it's quite interesting and maybe somewhat surprising. So Alaska here, that enhanced precipitation is not a feature of El Ninos in this counterfactual climate. It's really due to the SST trend and maybe the radiative forcing. We can look at this region of the Pacific Northwest and British Columbia. The drying is largely driven by the El Nino itself, but there is some contribution from the SST trend and radiative forcing change. This region over the eastern US is largely driven by the El Nino, but somewhat counteracted by the SST trend. So that's important finding. And then finally, I'll just spend a little bit of time on California since it has been in the news, shall we say, with all the atmospheric rivers and incredible precipitation in the last few weeks. So California in the El Nino signal itself is favoring, very wet California in DJF, and that is being somewhat counteracted by the SST trend. So even though the real world it was very wet in California, these experiments suggest that it would have been even wetter back in 1979, and it is very puzzling to even think about that could be, because we have a warming world. You would think you have more precipitation, not less. But that SST trend in the tropical Pacific is driving that high pressure over the North Pacific, which is then affecting storms into California. So it's a bit of a interesting situation, and I don't think it's really been kind of highlighted quite to this detail. So here I'm showing you some histograms for this California Southwest region. So kind of the region where you don't see stippling, so it encompasses California, Southern Nevada, Arizona, and New Mexico. I think that's pretty much our California Southwest region. So the top histogram, the gray bars are the control run in 1979. So that's just what the spread in the precipitation amounts relative to the mean of the control run in millimeters per day. That's what the atmosphere produces on its own. So that's just the internal variability driven by the atmosphere against which we are looking for an El Nino-induced signal. So the blue bars are the experiment, the top experiment that has all of the ingredients, the trend, the El Nino, and the change in radiative forcing. And consistent with the lack of significance that you see in that top map for that region, the blue and the gray bars overlap almost completely. There is no significant signal. But if you look at the counterfactual, the red bars, you can see that indeed on the positive end of the histogram, so the enhanced rainfall, you can see that that there's significantly more heavy precipitation events. These are monthly means. We haven't delved into daily. This is a 1 degree model, not an 1/8 of a degree model, which could even enhance the precipitation impacts even more. I think that would be super interesting to pursue with WRF or very low resolution CAM. And just to put it in context, we have the December and January anomalies for this region from the ERA 5 precipitation. And they're actually kind of in the middle of the distribution. We don't have February yet. So at least those 2 months were not that anomalous, at least compared to these red bars. Okay, so now the kind of last thing before wrapping up is to just give you a sense for what we're up against in terms of the probability of having a wetter California or any impact due to this internal atmospheric variability. So I'm going to focus here on different ways to characterize these probabilities. So one way is what NOAA does with this probability forecast. So what are the chances of falling in the lower, middle, or upper tercile of some control distribution? So we've computed that. So we take the control distribution and we divide it into thirds and then ask in our experiment how many ensemble members, what percentage fall within the upper, middle, and lower terciles. So here is a map of those probabilities for each of those terciles. So if you are just focusing us with that red circle for that region, California in the Southwest. So for that region, we have kind of 50 to 70% probability of being in that upper tercile in the counterfactual world. But if we look at the total world, the world that includes the observed trend and the change in radiative forcing, those probabilities go down somewhat, and that's because the SST trend in radiative forcing actually counteracts that signal in that region. So you can see, I won't point out other regions that are different, but you can see that these probabilities change due to climate change or due to the observed SST trend and the radiative forcing. And then we can also do probabilities for the effect of the observed SST trend and the radiative forcing change. And you can see that, say for California, the probability of being in the lower tercile just due to climate change. I don't like that word because that means I'm attributing the observed trend to radiative forcing, and I don't think that's quite right. But you can see that the impact of the observed SST trend and radiative forcing really would favor being in that lower tercile. So these are really interesting aspects that I don't think we'd have the luxury of getting at with 20-member SMILES and also doing this bias correction. So I think the AMIP is a good kind of way to look at this, although perhaps somewhat idealized the way that we've done it. So I'll wrap up by just, I love maps. I'm not as good as looking at the statistics. Maps is kind of really speaks to me. So I thought I'd just show you what I call these postage stamp maps. They're tiny maps, but you don't have to look at details. It's just kind of the sign. So what I'm going to show you is all 50 members of the AMIP. And I know some people hate it, but I like it. So this is the experiment, the original experiment, the SMILE, predicted SSTs, the observed SST trend, and the change in radiative forcing. And that little map in the upper right is the ensemble mean of the 50 AMIP runs. So that, we have a really good handle that is the force, the response to the SSTs that we've prescribed. So that's what we saw near the beginning of the talk. The ridge, that's the puzzling ridge that is sitting over Alaska, and then that low pressure that is sitting kind of in the central North Pacific. So the real world gives us one roll of the dice here, and the model will give us, and the model, we can use the model to see what the rolls of the dice might look like due to the combination of the SST force component and the internal atmospheric variability. So don't look at the details, just look at the variety of winter sea level pressure responses. I'll show you precipitation in a moment. Obviously, a lot of them have kind of a high pressure over Alaska and British Columbia, otherwise we wouldn't see it in the forced response, the ensemble mean. But a lot of them don't, and a lot of them have a big low pressure. And just for example, these two members are almost opposite, and they're all equally likely. These are just, these tiny initial condition perturbations. So that's just another look at probability forecasts, where you get the spatial information, not just in this point-by-point look. And then I'll show you the same thing for precipitation. So these are really small, I know, to look at, but I'm just highlighting those two members there on the left that had the opposing sea level pressure in the North Pacific, and you can see the whole West Coast could be wetter or drier depending on that circulation outcome. So there is a lot of variety. Is the model correct in its, amplitude of internal variability? Is it correct in the amplitude of its response? These are all open questions, but I think it's based on past work. I don't think it's too far off. And then I'm just superimposing in the middle here. We couldn't get the February ERA sea level pressure yet. It's going to come out in 2 days, and I will update this plot. I'm going to be super interested. But if you just look at December and January, it has a big low pressure, but doesn't mean the model's forced response is out of line, because there could be also a contribution from internal variability. And then here's the observed December, January ERA 5 precipitation. And, you know, we've done a formal test, and this does sit within the range of the model spread. So, okay, very last thing. So how did we do? So comparison with observations. Here are the SST comparisons. We were able to get the ERSST V5 data on Monday. So we've updated that through February 2024. So you have SMILE in the left, AMIP, and then the OBS on the right. So that's how what the SSTs looked like and how they compared with what was put into the AMIP runs and what was put into SMILE. And oops. Oh yeah, and here's the Nino 3, right, and I'm just showing you that the observed was 1.8, and that kind of sits between the SMILE and the AMIP rescaled SMILE. And here are the precipitation responses, and here ERA is just for December, January. Some similarities in the tropics, also some differences, and the exotropics I think are, you know, kind of roll of the dice. And then here's what the sea level pressure looked like, but that's just for December and January. Okay, I went kind of quick, but yeah, and then this is the difference between the AMIP and the OBS, and where there is stippling, it means that the model is not able to encompass the observations. So in these extratropical regions, there is no stippling. So the observations do lie within the ensemble spread. So, you know, at face value, I think the model is credible. All right, so thanks for letting us go a little long here. So just a few summary points. So the first is, I think it's such a nice opportunity, I would say, for, you know, expanding on the incredible SMILE results and skill to be able to piggyback and use AMIP ensembles to really get more knowledge of the predicted impacts and why they are occurring. And as someone recently said, as I mentioned at the beginning, we're putting skin in the game, and I really like that. So the forecasts from SMILE are very skillful for DGF and rival the NMME. And just summarizing what the CAM ensembles predict for precipitation over North America. Don't have to read the details. And then I thought most interesting part for me is this counterfactual set, and how the counterfactual really indicates that there's an important and complicated role for the observed SST trend and the radiative forcing changes. So it's not just El Nino as we used to know it. It is El Nino plus impacts from changes that we have observed. And again, these 50-member AMIPs are really insightful for these forecast probabilities. And we want to continue this kind of project, and maybe higher resolution atmospheric models would be great. And then once we get the SSTs, or now we're ready actually to run these AMIP ensembles with the observed SSTs and see how they compare with the model results. Thank you very much.
Thank you so much, Steve and Clara. Do we have questions in the audience? Okay, yeah, Dan, go ahead.
Thanks both. This is a really cool deployment of these tools. I was wondering if you had looked at the difference in the spread between the AMIP and the coupled simulations, and if that was the coupled interactions were part of what we're generating spread in the 20-member SMILE.
Yeah, great question. Haven't done that formally, but yes, since the SMILE, we're taking the ensemble mean SSTs, and SMILE obviously had, you know, plumes that diverge. So there should be additional spread in the 20-member SMILE just due to the different ENSO predictions. A separate question is whether air-sea interactions in response to the El Nino change the spread. And we've looked at that with earlier versions of CAM, and not very much, at least with the 1 degree, comparing pacemaker and aortic runs. But yeah, great question, thank you.
Other questions from that? Okay, we have A first and then.
I guess along the same lines, I'm not sure what additionally you would learn, but you could have chosen to use those individual forecasts from SMILE for the SSTs and
Right.
then drive the CAM ensemble somehow with that
Right,
ensemble, and then you just would have gotten more spread, I guess, and then.
but then it's so hard to parse.
Yeah, exactly, so I'm not sure what.
What's the internal variability, but yeah.
If you're trying to do real prediction, I guess you'd want to do something like that, as opposed to you're trying to do understanding here of the climate change forced response, right, which is a different, slightly different question.
Yeah, go ahead.
Yes, one of the conclusion we get is
Okay.
that we are getting like larger contribution from trend errors, and I think we can expect the contribution from trend errors going to get large as we as we have more climate change. And I want to hear like how like should we deal with this issue? And
Yeah.
is it like only assessed by the like bias correction, like post processing, or how
Yeah.
how should this affect the development of models?
It's a great question. Maybe I'll give a little bit of an answer, maybe Steve wants to. So I guess so if you take the uninitialized CSM2, say large ensemble, it has a enhanced warming trend in the eastern tropical Pacific, opposite to the observations. So that's what its rate-of force response looks like. The SMILE, these are November initialized SMILEs. So the trend in those is more like the observations. I may be wrong, but I think that is the case. So I think it's not the uninitialized CSM2. We have done actually a counterfactual, taking the uninitialized lens to forced trend to see the impact of that enhanced warming in the eastern tropical Pacific on these teleconnections. I have more analysis to do, so I wasn't ready to show those yet. And yeah, that's the big thing. If models are giving us the incorrect trend, then that's going to change their teleconnections. But these 1 month lead forecasts, I think the trend is at least of the same sign in the tropical Pacific as the observations. Is that, do you have more to say?
Yeah, and I would just add that, in our rescaling, we're weighting by the anomaly correlation coefficient. And so that goes down with lead time, partly because the model starts simulating spurious trends, right? So as we go further forward, our anomalies are just getting damped quite significantly, partly because of this trend issue.
Okay, do we have any last minute questions? All right, and do we have questions online? Okay, that's almost the top of the hour. Let's thank our speakers again for the See you next week.